So physics 2048, everybody? Nobody's at the wrong spot. Okay, so disclosure, we are live streaming this, so be aware that if you're talking to the audience that it might be picked up. So for this review, I have a bunch of practice problems I've made that have gone through kind of everything that you guys have done. Towards the end, there may be a couple questions that your specific professor may or may not have covered, so just be aware of that. The last questions kind of relate to the last chapters, and some professors didn't all go over that. So I'm going to go through all the questions. This review is posted on the Study Union WordPress as well as the Stark WordPress. And after I'm done, sometime today I'll upload my solutions. I'll scan them in. I'll go through everything, and then after I've gone through them all, if I still have extra time, I'll go back and I'll go over some concepts really quickly. Okay. So first problem. Snowmobile originally positioned with position vector 29 meters at 95 degrees counterclockwise from the x-axis. And then it has a velocity of 4.5 meters per second at 40 degrees. And then its constant acceleration of 1.9 meters per second squared at 200 degrees. And then after 5 seconds, find position vector and velocity vector. So basically, first thing we need to do is we need to break down all of our vectors that have been given to us into their components, because we can't really do any algebra or arithmetic until we have them in component form. So I'm going to do the position vector first. Actually, let me move it up. So if we want the x and the y for our position vector, we're going to do, for x, we're going to do 29 cosine 95 degrees. And just to draw that really quickly. So if it's from the x-axis and it's 95 degrees, so our x is going to be 29 cosine 95, and our y will be 29 sine. And then we break that down, get the numbers, so and then since it's a position vector, our units are meters. Moving on to velocity, we got 4.5. If my hand is getting in the way or anything, or if I need to rewrite anything, please feel free to speak up. Then we have velocity, so it's meters per second. And then our final one we have given to us is our acceleration. So first thing we'll notice is that no matter what we're doing with our vectors, we're always going to break down the same way. It doesn't matter if it's force, velocity, acceleration, position. We're always going to break it down just by using our sine and our cosine of the angles. For these ones, since they were all measured from the x-axis, it makes it specifically easy. Because if when we do our cosine for, let's say, the first one, the one I drew over here, since it's measured from the x, we always know that it's going to be finding this horizontal distance, which in this case, since it came out negative, means it was talking about this horizontal distance. If we're doing it from your different axes, you need to make sure you're using the correct sine and that you're using the right, using cosine or sine correctly, because it can vary depending on where you're measuring it from. So now to move on to the next part. So it's asking for after 5 seconds, find the change in our position vector and our velocity vector. So I'm going to start by finding the velocity after 5 seconds, since we're going to need that to find the position also. So we know our velocity final is equal to VO plus AT. So if we do this for x and y, so So initial, taking it from up at the top, and then pulling the acceleration down from above as well. And then doing the same exact thing for y. So then put this back into our vector form, since that's what it asked for in our question. And then meters per second. So to find our positions, we're going to also plug into our kinematic equations. We can do the same thing we did in this one, where we break it down into its two steps, to our x and our y, and then do it from there. So if we wanted to find our change in our x, let me move this up a little bit. We're going to do the same, one of our standard kinematic equations, so VOT plus 1/2 AT squared. And we have to make sure that we use our acceleration in the x direction and our velocity initial in the x direction. So plugging in from the top. So we found delta x. That's our change in our x coordinate for the 5 seconds. But it didn't ask for the change. It asked for where's its final position. So if we want to find the final position, we need to add our change to our initial position from up at the top, up here. And I promise not all my questions take up this much paper. This is, I think, the longest one, math-wise. So I'm going to do it over to the side. So if we want to find our final, the x direction, then we're doing our initial plus delta x. So it's -2. Okay, so now let's do the same thing with y, and then we're pretty much done. We just have to combine it back into a vector. So do the same formula for y. Okay, so we have delta y, and then just as we did over here with our x, we're going to do the same thing and find our final for y. Oops, I just wrote the same numbers on there. My bad. And then we get 35. And then combining those back into our final position vector. So there's our final answer for this question. Are there any questions on that question before we move?
So for these kind of questions, are we not supposed to do just find like the
So if you just find your final velocity,
that's good enough?
yeah, and this one, yeah. Since it asked for it in vector form, you're going to have to go through all the steps. But if it was just asking for, well, what's your final velocity at this point, then you could try to just do it straight through. The issue is that since your acceleration and your velocity are at different angles.
No, I mean like do like the square root of the x squared, y squared, and then find the angle.
Yeah. Yep, the angle, so for this one, the only thing to be careful of is that these are all both going to be at different angles. Since you have initial velocity and you have a constant acceleration, everything's going to be changing. So I would usually just breaking everything down is usually the easiest way to do it, to make sure you don't make any mistakes going through. So yeah, so like I said, that should be the longest one steps-wise. So for this one, we're spinning a ball at the end around a circle on a table, above a table. It tells us how high it is above the ground, and then it tells us the radius. When the string breaks and the ball lands 2 meters away, then find the radial acceleration of it. So let's just briefly draw a quick little diagram. So if this is our plane where our object is rotating, so our object is rotating up here somewhere around a point. It's saying that at some point here this snaps and our ball goes like this and falls to the ground. Tells us this distance is 1.2. Okay. So if we know how far it fell, the distance it fell, and we know acceleration due to gravity, and we know that there was no velocity in the y direction initially, then we can find how long it took the ball to fall from up here down to the bottom. And then if we use our time, then we can find its horizontal velocity, and then we can work back to its velocity when it was here. And we can find radial acceleration. So we're going to use the same kinematic equation we used for the last one. So like I just said, our initial velocity in the y direction was 0 because when the string broke, it had no velocity downwards. It was only moving horizontally. So because of that, we can cancel out this term, which then leaves us with t squared. And then if we start plugging in from what's given to us, we know that this was 1.2 meters. And we know that acceleration in the y direction is always gravity. And then from this we can solve for t. So
How do we know that there's no y velocity?
because it says at the top it's moving around in a horizontal circle,
Oh.
which means it was just rolling like flat as if it was on a table. So now that we have our time, we can find what its velocity was in the x direction. So using that same formula, oops. So using that same formula, we know that after the string is snapped, that our acceleration is 0 in the x direction because there's no reason for the ball to be accelerating unless we have air resistance, which we're not accounting for. So since there's no acceleration in the x direction, we get to say that this term is 0. Which means now when we plug in, 2 is equal to... Oops. I don't need to write the unit there. So now that equation, it's obviously a simple solve. So now we found the velocity right after the string breaks of our ball. And just
doesn't that right part all cancel out since acceleration is 0, 1/2 a t squared is 0?
for this one?
Yeah.
Yeah, that's why I crossed it out right there.
Yeah. So where does the 0.495 come from?
Because that's the time on this one. Oh, this.
There you go. All right.
Sorry, I crossed that out earlier. Thank you. So once we have our velocity right after it breaks, we can use that kind of infinitely small moment of when it's still spinning, and we can find our radial acceleration. Go ahead and move it up. So our centripetal acceleration is always, our radial, excuse me. It's always v squared over r. And we are given our radius in the question. So right there we knew it was 0.3. And then we just solved for our velocity, our horizontal velocity. So plug those values in. Over 0.3. And there's our centripetal acceleration when it's still attached to the string.
So when I was approaching this at first, I was thinking that you could say like velocity was change in distance over change in time.
Okay.
And like you could do the square root of x distance squared plus the y distance squared over time. Would that give you a different answer? Or like the reason that's wrong?
Because I think, if I'm understanding what you're saying correctly, that'd be saying going from this position at the top after it's spinning, like that, since you're doing Pythagorean's theorem basically, so you'd be finding the straight line rather than that curve downwards. Any other questions on this one? Pretty straightforward. Okay, so two-part basically. We have just two diagrams, which we can easily turn into Freebody diagrams, and then we can solve for our tensions in all our strings there. So to start this one out, I'm gonna be able to say that T3. I want to solve for T3 because T3 is the only thing hanging up the ball. So if I did a Freebody diagram at the ball itself, tension is the only thing pulling it up, and gravity is the only thing pulling it down. So because of that, I can say T3 is equal to force of gravity. And then just to write it out really quickly, sum of forces in y, T3 minus G. So once I know T3 equals Fg, I can solve for that really quickly. So T3 equals 49 newtons. So that's one of our three forces for our first one. So now to solve for the other two. I'm going to do a free body diagram at this point right here. Actually, let me draw on the inside. So I'm going to move our angles down. If we want, I can show that geometry, but otherwise I'm just going to skip it. So now if we write our equations at this point, which one? So I'll start with our x. So for our sum of forces in x, we have the x component of T1 pulling to the left. So I'm going to say that's negative. And then cosine of 40 degrees, since we're looking for the adjacent for the x direction. And then do the same thing with T2. And we know that these have to equal 0, since obviously this position isn't accelerating in any way. So from this, we can calculate one in terms of the other. So all I did is I just solved for those and divided out the other side. So we don't need this right now, but we're going to need it shortly. So we still have two unknowns there in that equation, so obviously we're going to need another one. So I'm going to do sum of forces in y on that same point. So for y, we have T1 is pulling upward, so it's going to be positive. And then T1 sine 40 degrees to find the y component. And then we also have T3 pulling downwards on the point. And there's, since it's going straight down, the component comes out to be the full tension. And then once again, we know it equals 0. So if we plug in T3, and I'm going to move it to the other side, we have two unknowns again. The same two as in the other part. So we can plug this down into here. I'm going to move this over. So now we've got everything in terms of T1, which means that now we can solve for T1 because we only have one variable. And this comes out to then we'll divide it to the other side. You get T1. What? Okay, so now we have T1 and we have T3. So, and we just need T2. Well, fortunately, we have the equation we found earlier, which is just way simpler to plug into than if we try to plug back into like this one. So, actually, let me write it to the side. So there's all three for the first diagram there. So to kind of recap really quickly on that one. So all we really did is we solved for T3. I'm trying to move up without cutting you guys off. So we solved for our T3, since we know that that's bearing all the weight of the entire ball. And then we used our sum of forces in X and Y to solve for our T1 and T2. So, moving on to the second one, or am I good to flip? Ready? Okay. Okay, so I'm going to redraw it really quickly. Okay, so let me just make sure I wrote everything the same. Okay, so it's going to be generally the same process as the first one. There's a small difference in this one, but we'll get to that in a moment. So, same thing as last time where T3 has to be equal to FG. Got it. Now, when we do our sum of forces in X and Y, yeah. So the really only main difference in this one is that since T2 is completely horizontal, it means that in the X direction, it's going to be having its entire force, so there's going to be no component of it. And then in the Y direction, it'll be 0. So then, where am I going to write this? So this one's even a little bit easier than the first one, because if you write out both your equations before you try to solve them, you'll immediately notice that this one we can solve for already. Because we know T3 is 98 when I'll move it over. Which means that T1 is just equal to 98 over our sine 60 degrees. Comes out to 113. So once we have T1, we can just plug right back into to this one. Oops. And then there's all three for that one. So these diagrams really just come down to finding which points to do your free body diagram at. And then once you have your free body diagrams, just writing your sum of forces in x and y direction and making sure that you have enough equations for the amount of unknowns you have. So there are some like harder ones in your book where you'll see there'll be more forces and you'll have to take 2 free body diagrams so you can get more equations. In reality, if you want to think about it this way, is that if we start with 3 unknowns, we're going to have 3 equations. So 1, 2, and then our third. It's just that our first equation is just basically nothing. So it just comes back to the whole, one of the biggest things you guys have to do in here is look at how many unknowns you have and how many equations you're going to need. Because if you're sitting there with 1 equation and you have 2 unknowns, you can stare at it all day. You're never going to get it. So moving on. Oh. Yes. Yes, I have a question later on that uses both of them. And I think that's, let's see. I think it's 6 or 7. 6. Or no, it's 8. Okay, 8, sorry. I'm just basically going through each chapter sequentially. So the later topics are going to be towards the end. And I do that so that the people that have professors that didn't go over the last 2 questions I have can leave if they have to or whatnot. So this is a pretty stereotypical question. You guys will see this a lot. So the 3 masses hanging, they're all connected. And then just finding what their acceleration is and then the tension in all the chords. The biggest thing you guys always have to remember in this is that your acceleration of all the blocks is always the same. Because if this block is moving, then this block also has to be moving, which means this block also has to be moving. They're tied together, they have to all move kind of as one. So if I'm doing a free body diagram of each one, I'm going to do it over to the side. Actually, before I can get going, there's one thing I want to go over, and that's that, actually, let me just go ahead and do this first, and it'll come up. So these are all moving, right? They all have acceleration, and I kind of need to account for that when I draw my diagrams, and I don't want to forget it when I do my equations. So I want to write it in here somehow now. So I want to say basically are blocks moving, accelerating up or down. So how do I figure that out? Well, if I look at the problem, because in reality, it doesn't matter which way I draw my acceleration on these blocks. As long as I draw that they're all accelerating the same way, if I guess that they're going the wrong way, then it'll get a negative answer. That's all that means. So if I say that they're going up, this one's going up, and that, this one's going right and that one's going down, and I get it wrong, that means they're all going the opposite way that I expected. So if I'm going to guess which way they're going, since it says M1 is 4 kilograms, this one is 1 and this one is 2. By applying a little bit of logic here, I can say that it's probably going to be this one's probably going to be going down and pulling this one up, since it weighs significantly more. So I'm going to say that this is accelerating down. And then I'm going to draw the other ones, actually. Give this one some room. So this block has, sorry, I should actually label this T1. T1 is pulling it to the left. T2 is pulling it to the right. And then I said it was accelerating to the left. We have gravity pulling it down. And we have the normal force going back up. So there's one more thing we have to account for here, and that's that it tells us the coefficient of friction at the top. So which way is friction going? Well, if we take what I said up here about accelerating to the left, that means that friction would be going to the right. And if I had drawn them accelerating the opposite direction, I would have drawn friction going the other way. So that's F of K. So right now that looks like a lot. But we can easily kind of make this a little bit easier on us, and that's that since there's only 2 things going in the y direction here, I should say 2, we can immediately know that f of n has to be equal to Fg. Because in reality, the only reason why we need our normal force in this one is because we have friction. We're going to need it when we plug into our friction formula later, so I'm just kind of getting it out of the way now so I can kind of simplify this down a little bit. And that was... do the same thing written down, right? Okay, so now for our last block. It should be square, but I'm also going to label these FG1, FG2, FG3, just so that we all know that they're different forces of gravity. Obviously, when we calculate force of gravity for this one, we're not going to use this one's weight. Hope that's pretty obvious here. And then we know that this one has to be accelerating up for them all to be going up and to the left. So, okay. So now we have to determine the acceleration and then the tensions, which will kind of go hand in hand here. So I'm just going to start kind of throwing out sum of force equations, since that's really what this is going to come down to. Is we know that we have, if we're solving for tension, both tensions and acceleration, we already have 3 unknowns. So we're already going to have at least 3 equations. So if I do our sum of our forces at mass 1, we know that our only things we have here is we have, I'm going to say, here, I'm going to write this way for now. I'll explain it in a second. So even though tension's pulling up in this one, I'm drawing it as negative because since I want MA to be negative or to be positive, and MA was going down in that case. Sorry. So if we look at this one, I just basically I made everything going down negative or positive in this one, just so that it keeps all my signs kind of nice and pretty. If I did it the more normal way, it'd just be the same thing, just with negative signs. So we can all see those are equivalent.
What's the subscript you're using for the summation of force?
I just said FM1 for mass 1.
FM1?
Yeah. Just because I want to label, have some way of looking back at it and knowing which one I'm looking at. So this is kind of a big idea, is that it doesn't matter which way I label these forces. If I say down is positive or up is positive, it just matters that I do it the same for that entire system. As long as I say in this block that down is positive, and I say that, okay, that means this is positive, and this is negative, then it's fine. But if I start saying that, oh, I want this one to be positive, so I make it positive, and then I don't correlate it to the other ones, then that's how you screw up your signs. So just make sure that you're always using the same signs. Doesn't matter which way you pick to be which. If you're worried about forgetting, draw it on your paper, because a lot of people will change the way they do their signs from normal, because it's like, oh, it looks easier in this question if I say down is positive, and then they forget about it halfway through their problem, and they screw up. So I'm just going to write that really fast, the top. That should also be 1. So just to kind of plug into this a little bit, I obviously can't solve it because I have a tension and an acceleration here. I have 2 unknowns, so I can't really go through with it, but I'm just going to write these down really fast. Also, as painful as it can be sometimes, a lot of times it's easier if you leave it in terms of your variables. So as much as I know everybody wants to always plug in, just remember that a lot of times you'll have stuff cancel out. And you might have problems where, I'll call you in just a second, where you have, they don't give you a mass or something like that. And then you're like, how do I solve this? I don't know. I have 2 unknowns here and I have 1 equation. Well, if you keep it in terms of your variables and don't plug in, you'll a lot of times find that it'll divide out. It's not the case here because we don't have an mass in our tension, but in general.
Is that T1 right below the sum of FM1? Is that negative or no?
This one I was just kind of showing that these are the same.
Oh, right.
So you don't really need this one. I should probably say this is correct, but not using it. I don't want people to be confused that that's wrong. But, so this is really as far as I'm going to take this one, because I have, like I said, acceleration, I have the first tension, so two unknowns, not doing anything with it anymore. So, moving into our next one, I'm going to go to FM3, because I don't really want to deal with this monstrosity yet. So, for our third one, it's pretty much going to be the same thing as the first one, except for our signs are going to be different now, since our acceleration is upwards. So if I say that positive is upwards in this one, here I can also write this to make it easy. So tension 2 is pulling up, gravity is pulling down, and it's equal to the acceleration upwards again. Or sorry, this was supposed to be 3. So I'm going to just try to, like I said, once again, just kind of plug it in a little bit, just kind of get it started. So you'll see they're like I said, they're pretty much the same. They're almost identical, just different signs and different variables. So now to do the not as fun one. And I'm going to specify that this is in the x direction. And I'll kind of go over that in a second, because since we did the y up here, because the y was very brief, the reason why I did that earlier is because we're going to need that in a second, so we're just going to plug straight in. So when I'm doing our second one in the x, I'm going to say left is positive, since that's the way our acceleration is going. And then if we're doing that one, then we're going to say, okay, we have tension 1 is positive, and pretty much everything else is negative. And that's all equal to our acceleration again. Okay, so now if I start plugging into this, so this is pulling this from up here, that our normal force is equal to 9.8, and then our mu is 3.35, and then also plug in this mass, which is 1, so. Okay, so now we have 3 equations and 3 unknowns. Surprise. And then that was, I'm just not going to calculate that right now. God, I should just not squish this. Sorry. Okay, so now we have, in our first equation, we have T1 and we have A. Second one we have T2 and we have A. And the third one we have T1, T2, and A. So now I'm going to try to take our first two, put them in terms of our solve for tension. So we have tension equals some number plus acceleration. And then once we have both of our tensions, we can plug both those formulas into the third one, and we'll get everything in terms of acceleration. And then we can combine all our terms, solve for it, and then we'll have acceleration, and then we can go backwards to our other ones. So if I go back to so M1 was 4, so 4A minus T plus 4 times 9.8. So move T to the other side and move A to the other side, and we get 4 times 9.8 minus 4A equals T. 1. That's important. So we have that one in terms of T1. Let's do the second one. T2. Equals 2a. Oops. Okay, so we got our two equations. Everybody still with me so far? Bearing through this. So from here, we're going to plug both of these back up. And now I'm going to have to actually do these really fast. So really quickly, just... Okay, so now plug that back in and plug this back in. So T1 was 39.2 minus 4a. There's T2, and then oh crap. Okay, so now everything's in terms of A. Now we can just have to do algebra, solve for A, and then it'll be our part A, and then part B, and then part C will be extremely quick. Excuse me. So A, I'm going to add the 4a to the side, negative 2a, adding it to the side. On this side we're left with 39.2 minus 19.6 minus 2.94. 7a is equal to whatever that number is. That looks right. Hopefully that number might have been math the same. Yeah. And meters per second squared. Don't forget your units. I know a lot of your professors will take off points if you don't put your units in your final answers. You don't, unless your professor says otherwise, you pretty much never need them through your work, but always put them on your final answers. Whether you do that while you're doing it or at the end, just it's always a good thing to double check.
Do you assume that the acceleration is not equivalent to the acceleration of gravity because it's not in free fall?
Yeah. Yep. Since this block, basically what we're saying with all of these equations is that, oh, this block would be in free fall if it wasn't for the tension. So the tension is basically what stops it from being in free fall, as well as one over here.
So it would always be less than 9.8 so like, is that like the way we can check it?
In this case, yeah. I don't think there's any possible way you could get one of these questions and it would be greater than gravity. So I think that's a pretty safe assumption. The only time you should ever really find acceleration greater than is if you have something like an external force. But since these are all kind of have to cancel out along the way, then that really can't be the case. Oh yeah. Yep, I still have the one part as well, so I'm going to try to make this find some space in here. So if I do this first one you have right here, 2 times 2.31. Oh boy, where am I putting the first one? Guess I'm putting it over here. I'm going to apologize in advance the fact that this is kind of, I bounce around all over the paper. When I post the notes, I'm going to post the version I'm using over here, and it's a bit more organized. And I tried to draw more arrows in that one to show where stuff's going. Okay, so pulling it from up there, we had T1 is equal to negative 4 times 2.31. And that gives us that T1 is 29.96 newtons. So, should we recap really quickly? This one kind of guides you through it because it tells you what order to solve everything. But I highly doubt your professors are going to be that merciful. So, whenever you have any problem that's asking for tension or a force, draw Freebody diagrams. They will give you more equations than you probably need for to solve your problems. And then you just have to figure out what variable you can get everything in terms of. So in this case, I saw that everything had acceleration. So if I plugged in, I could solve for everything in terms of acceleration and then find that and then plug back in to find our tensions. So you just have to be able to identify that, because if you try to plug in everything in terms of tensions, it will not be very pretty. Is there any questions on this one? Or move on? No? Okay, this one's nice and short to give you a break after that problem. String under tension of 50 newtons is spun around in a horizontal circle. Radius is 2.5 meters. Which is a very big radius for what this drawing is showing, but it's going at a speed of 20.4 meters per second on the table. And then it's saying that basically you pull the string down from below, and then that radius shrinks because you're pulling it inwards. And then asks you to find, or tells you that the distance, the new radius, and the new velocity. And then it says the string breaks at that point. So it's asking what's the strength of the string, basically. What's the max strength it can handle? So if we want to find that point, we basically want to look at it just like we do for a lot of our problems, that instant it breaks. So that last, nanosecond that it's holding on. So I'm going to draw a very poor 3D, try and attempt at a 3D diagram here. That's about as good as we're getting. So if this is our ball spinning around here, and we're saying that the string breaks at this point, then it's breaking when the point where it breaks has to be when it's equal to our centripetal force, since those are our only two forces that are going in that direction. So now, if we want to look at it, if we look at when it breaks, and we say that, okay, T equals, oops, sorry. This is when it breaks. So if you look at this moment when it breaks, we're told in the question the velocity at the new point was 51 meters per second, and we're told our new radius was 1. But it didn't tell us our mass. So we have to solve for our mass somehow. Well, fortunately, this problem gives us the conditions before we tighten to that string. So now if we look at initial also ignore the fact that this ball is going like way too fast, but I say this all the time, but if you guys ever look at the numbers they give you in your physics book, you see these, they're like breaking the laws of physics by the velocities these things are going. But anyway, so we're going to use the same formula. So T equals mv squared over r. So in the initial condition, before the string breaks, it told us the tension was 50, which is basically what is another variable we were missing in that first part, or in the breaking, the point when it's breaking. So we can now say, okay, that 50 is equal to m, and then it was going initially 20.4 meters per second, and it was 2.5 meters. So now we can solve for our mass. Oops, sorry. So we can solve for our mass there. So m equals 50. Oops. God dang it. Okay. Good. So once we find the mass, you can just take that, plug it back up there. See if I can do this without writing over everything. This is easy as that in this one. I pretty much can guarantee you in one way, shape, or another, they're going to give you, every exam is going to have a question with circular motion. And a lot of people don't like circular motion. Let's be brutally honest. Nobody does. You just need to know your formulas and know how to use them. It's really what it's all going to come down to. Like in this one, we all saw that it was extremely simple once you had your formula and you plugged in and knew what you needed to find. Best thing you can do is something that I haven't really been doing here is that as soon as you take your question, or go ahead.
Was the 51 that you plugged in, is that the question?
Yeah. Here, you can just go back to the top. So here, I'll just show you what I was about to say. So one of the best things you can do in these questions is look at this and just write everything down. And is like what this equals this equals this, because it's very easy to forget like what variables you have in a question, which is what you need to figure out which equations you can use. So for like this one, I would write probably like initial t equals 50, r equals 2.5, v equals 20.4. So once you have something kind of like this format, you can look at your formula sheet and say, okay, what formulas do I need? It makes it significantly easier. So at this point, you'd be looking through your formula sheet trying to find ones that had as close to that many variables as possible. And this should actually probably be different as force. And there is a question later where I'll talk a little bit more about that whole circular motion and all the kind of caveats to that. Any other questions on this one? Am I good to move on? Okay. Okay, another easy one. So, center of mass. So this one's just asking for the location of the center of mass of this U. So there's two things that are kind of really important in this question. Can anybody know what one of the two things is? So this is a word that you probably ignore in almost every question, and that's the uniform thickness. So does anybody know what uniform thickness means in our center of mass equations?
One part of it is not heavier than the other.
Yeah. So it's saying basically that none of this area has the same weight. And what that means is that you can use your area to say instead of mass. Because obviously we don't have any idea what the mass of this thing is. So when you look at your center of mass formula, which is like m1y1 plus m2. Yeah. So like when you do that formula, obviously you're given no masses in this entire formula or in this entire question. So you could sit here for 20 minutes trying to figure out where the heck you get a mass out of that. But what it means is that since it all has the same thickness, that you can just use your area instead of mass. So there's one other important thing with this question. That's that you don't have to waste your time doing half the question. So does anybody see something that can shortcut half the question? Yeah. So it's symmetrical. So there's a line of symmetry right here. And if it's symmetrical about an axis like that, you can say, okay, the location in the x direction for the center of mass has to be 50 centimeters, which is 0.5 meters. So now you already have half the question done immediately. This is a great way to waste a bunch of time during your exam, is by calculating that. So just watch out for symmetry. It's a great way for your professor to put a question on there that's really short but can make students take a lot of time on it. So now for the y, because we obviously can't do that for the y anymore. So I already wrote the formula over there, but I'll rewrite it down here. And that's that our location of our y has to be equal to the mass of a section. Here, let me actually do this first. So when you have a shape like this, you want to break it down into parts. These are called like composite center of mass problems. If you take further physics classes, you'll see them a lot more. And that's basically the idea here is we want to break it into shapes that we know where the locations of their center of mass, and we want to just basically add those together. So rectangles in this case. So in this one, I'm going to break it into chunks like this. And we can ignore kind of like that line now. So this is going to be my 1, my 2, and 3. So now when I write this formula down here, okay, so first thing we want to do is let's figure out our pseudo masses in this case. So for mass for 1, if we want the mass, and like I said, since we can use the area, let me actually write that up here at the top. I should probably write area. So if you want to find the area in this case for the first one, or the pseudo mass, we know that it's 0.1 meters this way times, so that's just an area of a rectangle. Hopefully we all know what an area of a rectangle is. And then for the second one's going to be the only one that could screw you up. So even though it's labeled at the bottom that's 100, realize that 100 is representing the entire length here, not the length that is now it's cut into. So if it's 100 at the bottom, and we know that these are 10 wide, so 10, 10, this is 100, that's 80. Hopefully we can also do subtraction. So 0.8. And then M3 is just literally the exact same thing as the first one. So there's all our masses. So that's basically half the problem, or half the work we have here. So now we have to have the location of the center of the mass in the y direction. Keyword y direction there. So we know that this location right here is 0, 0. So if we want the location for the center of mass in the y direction for our first one, anybody know where that's going to be?
21.
It's going to be, for this one, it's going to be 0.5. So it's for a rectangle, it's going to be right in the middle. So it's going to be right there, which in this case, since it's 100 centimeters tall, it's going to be 50 centimeters to the middle. So I'm going to start writing out our equation with our values in it. And then 0. Okay, and then the bottom one again. So, good.
How did you know that for the second section, the height of it was 0.1?
Because it's not actually explicitly labeled in here, and I regret that I didn't do that. I realized it yesterday when I was working through these. But you just kind of have to assume that since this entire shape is the same thickness bar, that it is. And that'd be something that wouldn't be labeled like that on a test. That was a mistake on my part that I didn't label this was 10 right here. But it's just you have to kind of just assume it because of the way the bar comes in, that they're the same thickness at the top and the bottom. So that's my apologies on that part. So if we know that this is 10 centimeters down here, where do you think the center mass in the y direction is for the second piece? it's going to be once again halfway up through it. So the halfway point in this one is going to be that little line right there. So that's 0.05. 0.05, yeah. Because, yeah, 10 centimeters divided by 2, and then into meters. Technically, you don't have to do this in meters. I did convert everything to meters while I was doing it. You don't have to do that because it doesn't tell you in the question or ask you to do anything with it. Just make sure that if you're leaving stuff in centimeters, that you're not doing anything with it afterwards. Because obviously, I can't just start calculating like forces or anything like that with centimeters. And then for the third one once again is exactly like the first one, so 0.1 times 0.5. And that's just over our areas we calculated over here. And then from that, our value comes out to 0.371. That's in meters. So if that's the one for the y direction, and then we know our x already, then I can say x bar, y bar is then equal to 0.5, comma 0.371 meters. And that's it. So recapping really quickly, main things to remember out of this one. Uniform thickness means that you can use your area to represent like the weight of each part. Obviously remember your formula, and then look for symmetry in the question. Break everything down into shapes that you can find the position of. So if I added like a ball on the end of this, it's still a very question that you guys can do. Because if there's a ball up there, I mean obviously I'd have to tell you a bunch of stuff about it, but all you do if you added a shape like that is you'd find the area of it, and then you'd find its center, which would obviously be the center of the circle, because it's a circle. So yeah, that's about it for that one. And then make sure that you're also doing everything relative to the axis. So in this case, we didn't have to do it because it was because of our x direction, because we had the symmetry. But if I did have to do that, then I would have to say, okay, for the x direction, the center of this one is right there, which would be 0.05. So for 1, 2, we'd have to say it's right here, so that'd be the 10 there plus our 40 here, or you could just say 50 to the middle. And then our third one would be going all the way over, so it'd be 95. So just remember that you're always doing it, oops, that should be 0.95. Remember that you're always doing it to the axis you're looking at. So make sure, in this case, our origin was right here. So if I'm trying to find the x in this one, then I have to measure from this point all the way over to the edge to find our distances. Don't just put in, oh, this is 0.05 because it's 0.05 to this edge right here. That's not where our center is. Go ahead.
Why is it 0.5?
For which one?
For like the height.
For the height of?
Wouldn't it be 0.05 for the first and the third one?
For the first one, since it's 100 centimeters up and we're looking for the middle is going to be like this line right there to find its center of mass. So it's 50 centimeters up from the x-axis. So if you looked at the y-coordinate of like this line right here, it would be 50 centimeters.
Sorry,
Yeah. Any other questions? No? Good?
Just like scoot it down so I can only see the answer.
Oh, sorry. Okay. So now we're getting to a lot more relevant stuff. Ooh, collisions. Okay. So classic bullet flies into a block. Our block in this case is going to be going upwards after it gets hit with the bullet. So we're going to have kind of two parts here. Ignore part A. I didn't mean to leave that in there. That was, once again, apologies on my part. But, so we're given the height that this block goes into the air after it's shot. So we have our block with a little bullet in it. I'm an artist, I know. And we know this is 22 centimeters. So it says it goes 22 centimeters into the air after the bullet is into the block. And then we want to find the initial velocity of the bullet. So this is a two-part question, basically, because we need to find where the block was when it hit. So right after the collision, that instant moment where the block is still here, but the bullet is now in it. And then from there, we can calculate backwards using a collision equation to find the velocity of the bullet before it goes into the block. Now, there's an important distinction here I want to make, because the first thing, the reaction a lot of people want to do is they want to just take energy, our potential energy here, and just say, okay, then that has to be equal to the kinetic energy of this bullet, which is wrong. So if we remember, for an inelastic collision, so this is inelastic in this case, since the bullet sticks in it, energy is not conserved. So please do not try to use energy to go from this moment to before the bullet was in the block. Don't go from this to this. That's very bad. So if we have an inelastic collision, the only thing you can use is momentum. Don't try to use energy. Versus elastic. If it's elastic and they bounce off each other, then you're fine. Do that. The way I always tell people to remember it is that if the classic inelastic collision is a car crash, so if you have two cars that hit each other, well, when you have two cars crash, they usually stick to each other. They usually kind of bend into each other and collapse. They don't just bounce off each other. Well, when you have a car crash, there's heat, there's a loud sound, there's a loud crash, and there's all that heat energy, all the metal is crushed together. So you lose all that energy in heat and sound, etc. Well, if you have two things that bounce off each other, there's no, you don't have to see two bouncy balls hit each other and they both get hot afterwards. That's not how that works. Just remember that you lose energy in an inelastic collision, so you can't say that you can't use conservation of energy to go through this. So what I'm going to do to solve this is I'm going to use energy to go from here to here, and I'm going to use momentum to go from there. I'll move my hand in a second. So that's how I'm going to solve this. God, my handwriting is awful. So, and the reason why we're going this way, obviously, is because we're solving for this velocity of this bullet. This question could be obviously given to you the other way, and it could tell you the velocity, and then you could go back to the height if you needed to. So, like I said, I'm going to start with energy. So, at the moment that this is at the apex, when it's not moving and it's at the maximum height, it says it's at 22 centimeters. So we know the energy after. Let me just move this down a little bit. We know that this is mgh for potential energy. And then we have to say that the energy at the end of this time here has to be equal to the energy here. Oops, sorry. Thank you. So energy after collision. So the one distinct thing I want to say here, bless you, is be very careful when you do this, because if you label this so first of all, let me just say that this is going to be 1/2 mv squared. So I'm saying this is 1/2 mv squared for this block right here. Now, if I say that this is 1/2 mvi, you have to be very careful doing that, because by the time you solve this, you'll probably have forgotten that vi isn't the velocity of the bullet. It's the velocity of this entire block, and that you still have work to do. So just make sure you don't just label every step, especially in multiple part questions. Don't just label vi v final, because if your final isn't actually the final velocity and your initial isn't actually the initial velocity, you can forget and then just stop a question before you've solved half of it. So we know the mass of the this is also going to be, I should write this first, is the block of the mass of the block and the mass of the bullet, since they're combined at this point. Which then cancels out. So divide that out, divide that out. So once we have that, we can plug in 2 times 9.8 times 0.22. Don't put it in centimeters. Once again, a great way to get your stuff wrong. More times than not, I bet your guys' classes will lose more points by not using the right units, not using the right signs, than that you guys will miss points by actually messing up the problem. Because those little things change a lot. If I leave that in centimeters, it will give me a very, very fast velocity. That block will be going like the speed of sound. Just make sure you convert all your units to the standards, meters, kilograms, etc. Like I said, even in that last problem, I converted the meters, even though I didn't have to, just because that's just tabbed at this point. You don't want to screw that up. It's not a fun way to lose points. So calculate the velocity. I'm going to label this as, I've labeled this as VB in my work that I'll post later, just to kind of, once again, make it very clear that this is not the velocity here. And that value was 2.07. So once again, when I did this question with somebody during one of my sessions like a month ago, and we labeled this VI, and they at this point they were like, "Oh, so I'm done," and they started to put in the answer, and I'm like, "No. It's very easy to forget that this isn't the velocity you're solving for. This is a velocity you need to solve for it." So now, like I said up here, I said earlier, is that we're going to use momentum now. So we know that our initial momentum, oops, so we know that our initial momentum has to be equal to our final momentum. Oops, sorry. Thank you. Appreciate that. So start off with block. The block at the beginning was not moving, so cross that term out. We don't need it. Velocity is 0. So for our bullet, our mass of our bullet was 5 grams, so that's 0.005 times VI is equal to 0.005 plus our mass of our block, which was 1.25, all times 2.077. So then VI equals, oops, god dang it. And there's our final answer, if we plug everything in. So, once again, most important thing I can say in this problem is if things stick together, oops, sorry, let me try not to cover that up. Do not use energy. It's really the most important thing I can say here is don't use energy when the things are sticking together. So, or to go from the state before a collision and after a collision. Obviously, like I said, you can use the energy afterwards. Sorry, if somebody's still writing that. To go from here to here because there's no collision going on there, but don't use it to transition through that collision period. If they bounce off each other and it's elastic, then go ahead, but just don't do it when they stick. inelastic collision, energy not conserved. If they ask you for your energy lost, then obviously you'll have to do it. But since the reason why we can't do it is because of that, is that we say, if we're doing like the energy of this kind of collision, we say our energy initial plus our ME lost equals E final. Oops. Equals energy. So this is what we say for inelastic. So this is kind of come back to why we can't do this, is because like in this problem, we have no idea what this mechanical energy lost is, so we can't use it. So yeah, any questions on this one? Okay. So the next one is probably, if I had to say, probably the hardest one in this packet. And surprise, it's circular motion. So we have this block on a ramp. So we know it's going to want to be sliding down, and then it gives us the moment of inertia is 8, and we say it gives us the radius of that little our roller up here, and then it asks us to find the angular acceleration of that wheel caused by the string basically pulling on it. So we're given the friction force. Notice our friction force is given to us in newtons. That's not something that happens a lot, so make sure you don't do that wrong, and basically try to use a coefficient of friction again. So the big question on this one is like, oh god, where do we start? So I always, once again, I'm going to kind of go back to what I said earlier and start doing sum of forces. We can do it for the block. We don't really want to do it for the wheel, because obviously the wheel is just kind of, we don't really know what's going on with the wheel. So if I do our force, sum of forces in y for that block. So we know we have gravity coming down. Making sure I'm good. We have tension going, tension going up. We have friction. We've got a normal force. And then we've got the fact that this is all sliding downwards. So pardon me being over the problem. So now if we want to plug this in, oh wait, sorry, this is supposed to be x, not y. Actually, I think the best way to write this. I'm just going to say sum of forces, because basically what I'm trying to do here is the sum of the forces along the slide. I don't really want just x or y, just because if you write it, okay, so let me say this first. So can we all agree that drawing, it comes out to like something like this, that drawing would be the same if I draw it like this. Can we agree that those are the same for force purposes? So this is something I would recommend for some of these slope problems, is draw it sideways, because if you try to do sum of forces in x or y on this, you're going to have a lot of sines and cosines, which just leaves you a lot more space to screw up. So to minimize that, I just recommend just rotating it sideways, and then all you have to do is now is the sine or cosine of this one force. So if I do our sum of forces here of this block, so I can draw that back, and I can say it's accelerating that way again. So now if I do it like this, I can say pulling downwards is, I'm going to say left is positive on that rotated one. And the reason why I'm saying that once again is because we know that our block is sliding downwards, so I want to keep the way we're moving to be positive. So we know that our f of g is going to have some component of that that's going down the axis, pulling it down. So in this case, we're going to have fg sine 37. So do you want me to go through that trig really fast? I don't know if that's something you guys need. Yeah, I can do it I'll do it really quickly. So really quickly, the trig here, because this is sine. Obviously, that's not, doesn't seem like the right, can feel kind of wrong in this one. But the reason I'm saying sine 37 is that, you know, this is f of g. So when we rotate this, so we know that this angle here between this is 90 minus 37, whatever that is. Now if I look at this one, so here, wait, yeah. So now this is this face, and we already found that this angle was 90 minus 37, which means that this is 37, which means the sine is sine of 37, what we need. Or you can remember that that's the right one in that case, which is probably easier than doing the trig on the test. Trig, another great way to screw up your test. Make sure you're using your right sine and cosine. Generally, cosine is x and y is sine, but don't check that in your problems. Because if it takes you 5 seconds to draw out the triangles and check your which angle is which and which sine or cosine you should be using, but you can lose a lot of points on it. So now that I've done that proof, we know Fg sine 37 is pulling us down. We know force of friction is going up. We know tension is going up. And then we know that we are doing MA at the end. So now I'm going to plug in everything we have right now. So M was that. So notice that in this one, force of friction was given to us in newtons, which means we don't need to do anything with our coefficient of friction. We don't need our normal force, which is why I rotated it like this, is so that I didn't have to calculate the normal force and waste time on another step. Because if I do it like this, then our normal force does nothing. So yeah, don't try to take that 30 newtons and forget that it's in newtons, and just assume that, just like all our other ones, that you have to calculate it through friction, or through coefficient of friction. So in this one, after I solve it out a little bit, it is okay, so two unknowns. Obviously we can't do it. So we have to find another equation. And also, oh crap, we don't have an alpha in this, which is what we're solving for. So we have to have a third equation, because we're solving for angular acceleration, which that is not. Remember that A is not angular acceleration, it's linear. Well, we also know our centripetal acceleration is our radius times alpha. That's a formula we have given to us somewhere. So from this we can say that A equals 0.4 alpha. So there's the second equation. So now we can get rid of our linear acceleration and get our angular, which is what we're solving for. So now we just need a way to get rid of tension and get it in terms of angular acceleration. So the way we're going to do that is torque. That formula that nobody loves to see. So we know our torque, So we know our torque is equal to our moment of inertia times alpha. Our moment of inertia was given to us as 8. We have alpha. Now, we're once again probably thinking, well, why do we care about torque? We don't have T, that's not tension. Well, since, if I go up here really fast, so this force is pulling on that wheel and causing it to rotate. So if I draw the wheel down here, there's some force, there's tension going off like that, pulling the wheel, right? Well, we know torque is our radius times the force that's exerting on it from that, what's the word I'm looking for here? I have a brain fart, perpendicular to it. So you know that our torque, our tension times our radius has to then be equal to, and now we finally have enough stuff to solve. So we get tension in terms of alpha, so divide the radius out. And this comes over to T equals 20 alpha. So now we plug this into here, and we plug this into here. And then I'm going to just kind of draw that down here. 28.978 minus 20 alpha is equal to 4 alpha. And I just wrote A. So 24 alpha is equal to 28.978, which then means that alpha is 1.207 meters per second squared. We forget that too. Okay, so I do want to discuss this problem more, and there's a few things. Oh, go ahead.
In the topmost equation, the f of the block, that 10a, that's the acceleration of the block.
Yes. Yeah, because it's just ma. So it's the acceleration of the block linearly down the edge.
So why is that 10a the same as the a is the r alpha?
So since it's attached by a string, it means that the if we have a rotating circle and we have a force that's on the edge of it, when we talk about our linear acceleration, we're talking about our acceleration like at the edge of that circle, right? So if the string is attached to that, then it means that that acceleration has to be applied right here. So that would mean that that has to be equal to the tangential, that's the word I'm looking for. The tangential acceleration of the circle.
But that's not always true where the tangential acceleration equals the centripetal acceleration.
So, yeah, no, I was using the wrong term when I was saying centripetal earlier. So when we're looking at our tangential is what we're using for our torque. Because centripetal would give us a zero torque because our R would be zero in that case. But since our tangential in this case has to be equal to the acceleration of the block, because the block has to pull the string, which then has to pull the wheel, we can use that tangential to go back to find our torque, is basically what I'm trying to say. Okay, so I'm going to come back to this and discuss like a bunch of stuff about circular stuff, but I want to make sure I get to the other two problems first.
How did you find 20?
For this one, because the R was given to us up here is 0.4, or sorry, 0.4. Right, I did do that math right earlier, right? Double check. Yeah. So then 8 over 0.4 is 20. Oops, sorry. Yeah, I just plugged in the radius. Okay, and the last two are pretty short, so I'm just gonna try to burn through them as quick as I can, and then I really want to come back to this problem and discuss this stuff some more, but I want to make sure I get to the other ones. These last two are the ones that your professor may not have on the exam, depending on who you have. And before anybody asks, I don't know which one is which. It's just basically if you've covered this material, then expect something on it, which is why I made these not super complex problems.
What chapter?
I'd have to look at the book. It's the gravitational chapter. The last two questions are gravitational questions. The second, the one after this has a little bit on rotational energy and angular momentum. So that one kind of relates a little bit back more. But this one is purely a gravitational energy question, or gravitational force. So this one saying we have 3 uniform spheres. Gives us the coordinates of how far apart they are, and then it's asking for the sum of the forces on that center, this one right here. So, before I start, our gravitational force is equal to gravitational constant times m1 times m2 over r squared. So r squared is just r, so g, first of all I should say, is an ugly constant. And then r is the distance between the two between the two particles. So really all we're doing is we're solving for these two forces, and then we can just put them in, combine them into a resultant force and writing that vector, that resultant force. It's pretty straightforward. So if I do f of 1, 2, so that's the force that's this force right here, the one exerted by the particle 1 on particle 2. And then I say it's 6.67 times 10 to the negative 11 times the two masses and then over their distance. So the distance here is since it's 0, 3. I don't have to really do any Pythagorean theorem there since it's just one distance. So I can say they're 3 meters apart. So 3 squared. And this is upwards because the force is pulls them together. So remember this force is exerted on both these two particles technically. So it's basically just saying that's the force pulling each of them towards the middle. And this comes out to 5.93 times 10 to the negative 11 newtons. So very small, but it's a gravitational force of two tiny particles, so I'm not really surprised. And then our f of 3, 2, so that's the one going between 3 and 2. Same deal, 6.67 times 10 to the negative 11 times 4 times 6 over, and then the distance, since it's negative 4, we can just, since it's just a negative 4 and there's no y component, once again, we don't need Pythagorean. Since it's over negative 4 squared, and this number comes out to 1 times 10 to the negative 10. And then just to combine these really quickly, this is also to the left. So if we want a total force, since we have one that's in the y direction and one in the x direction, we don't really have to break it into components or anything and do any vector stuff that we did earlier. So I can literally just combine these to say that f is let me just throw an I on there. Newtons. And there's our final answer. So like I said, this one's pretty straightforward. Any questions on that? Like I could have added more to this question to make it more complex, but really all I could add is stuff to make it so you had to do vector analysis and like to make your vectors into components, and since we already covered that, that didn't really seem like a point. So last one, and then I want to talk about that the torque question really quickly. So two astronauts swinging around in space, having fun, I guess. It's asking, this one is a question that's all in variables. It doesn't give you any numbers. And the reason why I did this is because I can pretty safely say that all your professors will probably put one on your test where you won't be given any numbers. And I know for some people that just breaks you inside. So to kind of go through this one. So it's asking for, they both have a mass m. The rope is length d. We don't care about the mass of the rope, and then they're circling each other with this at speed v. Treating them as particles, calculate the magnitude of their angular momentum, the rotational energy, and then it says, okay, if they shorten the rope, then find it again. So angular momentum. So I'm going to say Li because or L1 because they change it in the middle of the question. So we know that our one formula we have for our angular momentum is just mvr. So if we have mvr in this case, and we can say that, okay, the masses are the same because they both have the same mass. We can say they have the same velocity, and they have the distance between them is d over 2. And that's really all we have to do for that. It's truly that simple. Because that's the radius between them. We want radius, not diameter. So Now the second part is rotational energy. So we know rotational energy is just our 1/2 mv squared. But we have two of them. So we have two astronauts, so we're going to say 2 times 1/2 mv squared. Rotational energy then just equals mv squared. And those are both variables that are given to us, so we can leave it like that. We don't have to replace anything. And then it says they pull the rope together, so they pull the distance to half of what it was. What's the new angular momentum, new speeds, new rotational energy? So angular momentum, just like normal momentum, must be conserved. So we can say that our new angular momentum is equal to our old angular momentum, which means that L2 is just, I'm going to say, and I wrote V0 on here to show that it's the initial one, not the current velocity, the new velocity. And then what's their new speeds? So if we know that this is we know that their angular momentum equals that, and we know that angular momentum equals mvr, we can kind of plug those two formulas together that we did up right here, and form the new one. So we know that L2 has to be equal to mv2r. Then replace this with mv, I should also write that as v1 actually. Keep everything consistent. Now it would be d over 4. So I replaced the r with d over 4 because it was d over 2 before, and we made the rope half as short, so d over 4. The m's cancel out, the d's cancel out. If we multiply, we're looking for our rv2. So when we cancel that out, cancel this, and we multiply the 4 over, and we get 2v1 equals v2. And then the last part is just the new energy. So rotational energy, still the same formula. Once again, we still have two of them, 1/2, so I'm just kind of reusing that formula up there and not recalculating again. Plug in our V2, and we get 4v1 squared. So the main thing here is just remembering which variables you have given to you that you can use. So like I would write at the top here like d, m, v, and then remembering those are the only things I'm allowed to use, and making sure that all my formulas come out in terms of those values. So really quickly, so we still have like 15 minutes, but I'm going to leave some for cleanup and stuff. I want to talk about that torque problem. Oh, sorry. There's all those. So, in these problems, we all know that it's a pain to work in circular motion. We don't like using, all these new variables like inertia and angular acceleration, angular velocity, all that. But in reality, if you look at your equations, you'll see that they're all the same. Everything comes out to be the same. And what I mean by that is that, so in linear, we have a distance, right? We have like delta x. In circular, we have, we usually use our radians if we're talking about distance. So we have like radians. In linear, we have a velocity. In circular, we have w. And if you look, like our velocity over here is v equals, our delta x over some time. Over here we have, this is equal to our change in radians over t. Over here we have a, over here we have alpha. And what you'll see is if you start using these formulas, they're all the exact same formulas, but they all have equivalent variables in the other form. So Over here we have force, over here we have torque. Over here we have mass, over here we have inertia. And if you start looking at all your formulas, they're all literally exactly the same, but with the corresponding variable plugged into it. So, I'm trying to think of, I don't think I have any written down with me. So, like, really it just comes down to, actually let me use one of the ones I have over here. Okay. So, for example, we had torque. Torque is equal to our inertia times our acceleration. Well, if I just said a minute ago that torque is the same as force, and I said that inertia is the same as mass, and I said that alpha is the same as A, it's the same formula. We're all familiar with this formula. Your same thing works with kinematic equations. You can do all of your kinematic equations in circular coordinates if you just plug in the corresponding variables. It's really just remembering those few weird cases of how to convert from one to the other. That's really all you need to really have ingrained and memorized. So just if you can remember that these, just don't get bogged down by the fact that there's all these new variables that you just don't want to use and that you don't remember and all that. And yeah, that's really all I have to say on that, is that if you look at your formula sheet, you'll see that all of these correspond to the same things. So with that, I'm just about done. So before everybody runs home, this is something we have to have done. So QR code, just scan it, and there's a little survey they make us all do. So just fill that out, please. I'd appreciate that. Does anybody have any questions?
Back to question 9.
Yeah. I should slide this to the very top. Okay, so 9. Oh well.
So you're posting the solutions on
Yeah.
too?
Yeah. So do you guys know the WordPress for SARC?
Yeah.
Okay. I'll post it the same place as my review and where our hours all are. It'll be on there. I'll try to post it today. Yeah. Here, let me write it down back here. It's, I believe, UCF's. That should be the site. Yep. It's just the WordPress site for UCF SARC, if you have to Google it.